Hello and good day. This is Dr. Fredericks, and today we are going to be talking about the chi-square analyses. Thus far in the course, we've been talking a lot about analyses that test hypotheses about specific population parameters. And so because these tests are all concerned with parameters and require assumptions about parameters, they are called parametric tests. And so there are assumptions that are associated with parametric tests. And for one, they require a numerical score for each individual in the sample. And those scores that they require, the data needs to come from a ratio interval scale. Also, there's an assumption that the population distribution is normal and also that there is homogeneity of variance. And so if we think back on the ANOVAs that we conducted previously, we know that the independent variables for those ANOVAs were categories or nominal level variables. And we know that the dependent variables or the data that we've been working with previously were measured on an interval or ratio scale, right? And so thus previously we've been focusing on parametric tests. And so when the assumptions of parametric tests have been violated, there's several options or techniques that can be utilized to parametric tests, and these alternatives are called non-parametric tests. And so the chi-square tests are a type of non-parametric test, and essentially they allow us to determine if what we've observed in a distribution of frequencies differs significantly from our expected frequencies or what we would have expected. And so there's two main types of chi-square tests. We have the chi-square goodness of fit, also known as the one-way chi-square, and we also have the chi-square test for independence or the chi-square test of association, also known as the two-way chi-square. The chi-square goodness of fit test is utilized when we have one categorical variable with multiple levels. And it essentially assesses the fit between the data the researcher has actually collected, and that's denoted by an italicized F and the subscript O, right? So that's the observed frequency, and the data the researcher would expect if he or she had collected the data from the intended comparison group, denoted by italicized F and subscript E, which stands for expected frequency. And so for the goodness of fit test, the null hypothesis specifies that the proportion of the population that should be in each category. And it's either one or two things typically with the hypothesis, the null hypothesis. It's either one, that the null hypothesis is stating that there's no preference among different categories. And so in this case, it's saying that the population is going to be divided equally among the categories. Or two, the null hypothesis can state that the proportions for one population are not different from the proportions then are known to exist for another population. And so here is an example of what we're just describing. So here we have one variable, one categorical variable, eye color, with four categories, right? Your eyes are either blue, brown, green, or other. Other is probably a combination of three, I'm assuming. And so here you have a frequency distribution. And based on what we see here with the frequency distribution, we know that we have a total of 40 participants or subjects in our sample. How I know this is if we add all the frequencies together, 12 plus 21 plus 3 plus 4, we get 40. Essentially, a researcher in a situation like this may have simply counted of their sample of 40, how many of these individuals had blue eyes, how many of these individuals had brown eyes, and so forth. With this in mind, if we go back to the previous slide and look again at the null hypothesis, right, it specifies the proportion of the population that should be in each category. And what we're talking about in terms of what should be in each category, we're talking about our expected frequencies. And so if we look at the first option, again, the null is saying that there's no preference. And so among the different categories, you're going to have equally divided frequencies. Whereas the second is saying that there's a specific proportion that we may know exists that we want to have as our expected frequencies. And so if we apply that to this example, the first option for null hypotheses is that, well, there's no preference, right? And so, or there's no bias. And so eye color would be expected to be equally divided among the categories. And so if we know there's a total of 40 participants in our sample, we're saying that 25% of all of the participants are going to fall within each category. Thus, you would have 10 individuals in each category expected, right? And so the second alternative for the null is that there's a proportion that's known. And so let's say we wanted to compare our sample against a population of individuals that we assessed eye color on, or maybe previous research has assessed eye color on. And so here I have listed the proportions, the percentage of individuals from each group from the entire sample and how that breakdown looks by category. The chi-square statistic, again, measures how well the data or the observed frequencies fit the expected frequencies. And so the symbol for chi-square is this Greek letter chi and the superscript 2. And so essentially we are taking the sum of the difference between our observed frequency and expected frequency squared divided by our expected frequency. Now for the chi-square test of independence, also known as your two-way chi-square. This chi-square uses the frequency data from a sample to evaluate the relationship between two variables in the population. Again, if you think about two-way analysis of variance, we were looking at two independent variables. And in this instance, for the chi-square, we're looking at two variables in the population. And so each individual in the sample is classified on both of the two variables, creating a two-dimensional frequency distribution matrix. And so the test is called the test of independence because the null asserts that the two variables are independent of each other. And if two variables are independent of each other, then one can assume that there is no relationship between the two variables, or these two variables are not associated with one another. And so here we have an example in which we could compute a two-way chi-square in the event that we wanted to inquire or test to see whether there's a relationship between personality type and, let's say, your favorite color. And so here we have a 2x4 contingency table where we have two variables, one variable with 2 levels and the other with 4. And so within the contingency table, the numbers that you're seeing are frequencies that represent each of the categories or the combinations, right, of the levels. And so for instance, we can see here that there are 25 individuals whose favorite color is red and who are also introverts. So within you have the frequencies of the different categories, and outside the contingency table, what you're seeing here are your sums, right? We have column sums and we have row sums. And to move into effect size, previously you all learned about the phi coefficient or Cramer's phi being appropriate in regards to looking at association between two nominal variables. And so phi is a correlation, and it measures the strength of the relationship and thus provides a measure of effect size. And so as stated before, Your chi-square test of independence or test of association is testing to see whether these two variables are independent of each other or if there's a relationship between these two variables. And so phi is a correlation that focuses on the strength of the relationship. So does a relationship exist and how strong is this relationship are two different questions. And the matter of strength is where your effect size comes in. And so the value for the phi coefficient can be computed directly from the chi-square by using this formula, where you take the square root of your chi-square statistic and divide that by the total number of individuals in your sample. And this gives you, again, a measure of the strength of the relationship between two variables. Now, when we're looking at a chi-square test that involves a matrix larger than a 2 by 2, a modification of the phi coefficient known as Cramer's V or Cramer's phi can be used to measure the effect size. And so Cramer's phi is essentially the square root of your chi-square statistic divided by n, the number of participants or subjects in your sample, and you're multiplying that by L minus 1. And L is the number of rows or columns, whichever is smaller of either. And so thank you very much for tuning in and look out for the next statistic video.